LLMs are incredibly smart, but they don't actually read words like we do. To a computer, everything is math. Today, we're looking at the bridge called tokenization, the process that turns our messy human language into structured numerical data. At a technical level, an LLM processes text in small units called tokens. This matters because how we break down a sentence determines how well the model understands context, tracks long references, and stays efficient without wasting memory. There are three main ways to slice up language. We can look at individual letters, whole words, or something in the middle. Choosing the right path is the first step in building a model's vocabulary. This is the most basic method where every single character is a token. It keeps the alphabet or vocabulary very small, but it's hard for the model to learn the meaning of long words because it has to look at too many tiny pieces at once. Here, every unique word is its own token. While this is easy for humans to understand, the vocabulary becomes massive. Millions of words. If the model sees a new word like unrunnable that isn't in its dictionary, it completely fails to understand it. Most modern LLMs use Subword Tokenization. It breaks common words into one piece but splits rare words into meaningful subunits. This allows the model to handle any word, even if it has never seen it before, by looking at its familiar parts. BPE is the most popular subword algorithm. It starts with individual characters and iteratively merges the most frequently occurring pairs into a new single token. It's like a puzzle that builds its own pieces based on how often they appear together. Similar to BPE, WordPiece is used by models like BERT. Instead of just merging frequent pairs, it merges pieces that increase the likelihood of the training data. It's a slightly more mathematical way of ensuring the tokens are as efficient as possible. Unigram takes the opposite approach. It starts with a giant vocabulary and keeps removing the least useful tokens one by one. It's a top-down method that focuses on keeping only the most meaningful parts of a language. To handle every possible character in every language, some models tokenize at the byte level. This ensures the model never sees an unknown token because every character in existence can be represented by basic bytes. There is always a trade-off. A massive vocabulary makes it easier for the model to speak, but it makes the model's brain, the parameters, much heavier and more expensive to run. Tokenization must account for Zipf's law, which states that a few tokens appear almost all the time, while most tokens are very rare. A good tokenizer ensures it doesn't waste precious space on tokens that are hardly ever used. Modern tokenizers must be global. They use Unicode to ensure they can handle every script on Earth and even emojis. A single emoji might be one token or split into several bytes depending on the model's design. Believe it or not, Whitespace is often its own token. How a tokenizer handles spaces, whether it attaches them to the start of a word or keeps them separate, drastically changes how the model perceives the structure of a sentence. Numbers are tricky. If you tokenize 199 and 1999 inconsistently, the model might struggle with math. Engineers often use special rules to ensure numbers and dates are broken down in a way that preserves their mathematical meaning. For coding agents, tokenization is vital. Brackets, colons, and indentation must be preserved as tokens. If the tokenizer messes up a URL or a code block, the agent won't be able to execute actions correctly in the digital world. A major pitfall is using a different tokenizer during use, called Inference, than the one used during training. If the dictionary changes even slightly, the model's predictions will turn into complete gibberish. Consistency is the golden rule of tokenization. To wrap up, tokenization is the essential first step in the LLM loop. By breaking text into subwords and bytes, we keep the vocabulary manageable while giving the model the ability to reason across any language or data type. We are moving toward a future where everything, vision, voice, and text is tokenized into a single omni-stream. This will allow agents to see and hear the world with the same mathematical precision they use for text. Thank you for watching.